Hi everybody, I'm Vincent. In this video, I'm going to present research I conducted with Brent Hecht that studies conscious data contribution, a way for users to exert data leverage against tech companies. The backdrop for this work is that there is growing concern about the serious negative societal impacts of data-driven technologies operated by large tech companies, both in the media and within academic communities. Intelligent technologies have been linked with economic inequality, which is itself associated with many societal harms. Moreover, increasing attention has been paid to the ways tech companies may be harming privacy and democracy, among other concerns. However, existing power dynamics between the public and tech companies limit the public's ability to change tech company behavior. Attempts to exert leverage against tech companies through consumer protest, for instance boycotts, must contend with the market power wielded by large tech companies. To give a quick outline of this presentation, I'm now going to go into more detail about the background behind the data leverage concept. Then I'll go over the experiments we conducted, our results, and discuss their implications. In this extended abstract, we introduce and explore the data leverage concept. Data leverage is the power to influence a tech company held by those who implicitly or explicitly contribute the data on which that tech company relies. One way of exerting data leverage is through data strikes, when users withhold or delete data from a company they wish to exert leverage against. We studied data strikes through simulations in a 2019 web conference paper. An alternate form of data leverage, which we introduce in this extended abstract, is conscious data contribution. Users give data to a target's competitor. The idea of data leverage builds heavily on an earlier concept, data as labor. A variety of work studying data as labor has highlighted that users of tech companies play a crucial role in generating valuable training data to fuel intelligent technologies. This data labor is indeed a huge component of the success of these technologies. This idea has appeared in books like Who Owns the Future and Radical Markets, as well as in recent academic publications. It's also a topic that my lab, the People Space and Algorithms Research Group at Northwestern University, has also researched quite a bit. More generally, any case in which tech users, the public, generates or contributes to data used to train intelligent technologies can be seen as an instance of data labor. Indeed, for many companies, all users are simultaneously data laborers and consumers. Both roles contribute to company profits, so both roles are potential sources of leverage. Anyone who engages in data labor also has the capacity to withhold this data labor. Historically, laborers have withheld their labor as part of a strike to exert leverage. Thus, withholding or deleting data labor can be seen as a data strike. Data strikes are potentially very effective. In our prior work, for instance, we found a data strike by 30% of users of a small recommender system could take the system's performance halfway towards the unpersonalized baseline. However, data strikes must also contend with the diminishing returns of data. A system with billions of data points is likely to see very little impact from a small strike. Furthermore, a user who participates in a data strike hinders their own ability to benefit from ML systems. Someone who deletes or withholds their data will receive only unpersonalized results from any personalization systems. So that's where conscious data contribution comes in. Imagine we have some participants, a group of users who share some concern about a tech company's values or actions. Their target is a large tech company. While they might cut off their data contributions to the target as part of a data strike, this data strike might be too small to create a noticeable impact. However, perhaps there exists a small tech company with similar services, and the small company has values or actions in alignment with the participants. By contributing data to this small company, the participants take advantage of conscious data contribution. They boost the performance of small code's tech, and in turn create more competition for large code. As I'll illustrate later in this presentation, this alternate form of data leverage takes advantage of diminishing returns instead of fighting an uphill battle against them. A small data contribution could have a disproportionate effect on small code's ML performance. To situate CDC, we can think about existing tactics. Whereas the data strike framing is inspired by labor strikes aimed at punishing an employer, CDC draws on conscious consumerism, a tactic aimed at rewarding a company. At the same time, CDC can also exert leverage through increased competition. To illustrate, let's consider a simple example. A plot of the relationship between machine learning test accuracy on the y-axis, shown from 0 to 1, and what fraction of a data set is available. If 20% of users delete their data as part of a data strike, here, this has a minimal effect on the classifier performance. However, if 20% of users engage in conscious data contribution and give their data to a new small company, they could bring that small company's performance from 10%, the random guess baseline, up to 80%. CDC hugely reduces the performance gap between the two companies. Next, I'll talk about the experiments we conducted. I'll start with the premise of our simulation experiments. We define two companies, Large Co, the target of protests, and Small Co, a small competitor of Large Co that protest participants also support. Small Co starts with no data, while Large Co starts with a full benchmark dataset. Large Co loses data from data strikes, while Small Co gains data from conscious data contribution, CDC. We consider three scenarios. First, participants only data strike. Second, participants only engage in CDC. And third, a scenario in which participants jointly engage in a data strike and CDC. In other words, they delete data from Large Co while giving that same data to Small Co. The purpose of these simulations is to see how much Large Co's performance decreases and how much Small Co's performance increases. Then we compare the relative effectiveness of data strikes and CDC. How effective are these tactics for exerting data leverage? The simulation effectively follows the procedure used to study learning curves in machine learning. You take some sample of data, retrain from scratch, and evaluate performance. In order to compare the effectiveness of data strikes and CDC with different size participation groups, we defined a measurement, data leverage power, or DLP. To compute DLP, we first identify the baseline performance, for instance, the performance of a random guess, and then the best case performance for each given machine learning use case. For each ML use case, Small Co's performance starts at the baseline, while Large Co starts at the best case. Then for CDC, we look at the fraction of the way from baseline performance to best case performance that CDC boosts Small Co. So with no participants and thus no data, DLP is 0. It went 0% of the way. If Small Co gets all the data needed for best case performance, DLP is 1. Imagine that the baseline accuracy for some ML task is 50% and the best case is 90%. If CDC brings Small Co up to 70% accuracy, DLP is 0.5 because Small Co got halfway to best case. For joint CDC plus data strike scenarios, DLP is instead the fraction of the way from baseline to Large Co's data strike inhibited performance. In other words, in this case, DLP is a bit higher for a given group size because Small Co's performance improves while Large Co's performance goes down. Finally, for data strikes only, DLP considers what fraction of the way from best case to baseline a data strike takes Large Co's performance. In this case, DLP is 1 when Large Co loses all its data and is reduced to baseline random guess performance. Just to illustrate this idea a little further, here we have a quick example. In the top half, we can see DLP goes from 0 to 1 as CDC size increases and Small Co's performance approaches best case. On the bottom half, we see DLP goes from 0 to 1 as data strike size increases and Large Co's performance approaches random guess baseline. So what are the benefits of calculating data leverage power as opposed to, say, looking directly at classification error in the different scenarios? Well, DLP is agnostic to ML evaluation choice, which varies with ML use case. For instance, regardless of whether a model is evaluated with root mean squared error, classification accuracy, hit rate, or something else, we can always calculate DLP and make comparisons across use cases. DLP also makes it much simpler to compare data strikes and CDC. As I'll mention again at the end of this presentation, it's useful to also consider the ML evaluation metric from which DLP is calculated. Ideally, we'd even consider the cost of specific errors, like the cost of a false positive and the relationship between improved performance and outcomes. This is something we're looking into for future work. In this project, we focus specifically on DLP. In order to select ML use cases for our experiments, we sought well-studied tasks with publicly available high-performing implementations. We use these public implementations for our learning curve-esque data leverage simulations. In brief, the 4 use cases were recommendation with movies, recommendation with Pinterest items, classification of images, and classification of text. I recommend checking out the specific references in the extended abstract for more detail about these datasets and the implementations that we used. Now I'll talk about what we found. This slide shows our experiment results for a single use case, movie lens movie recommendations. First, the left-hand plot shows DLP. On the y-axis, we have DLP ranging from 0 to 1. 0 DLP corresponds to a data strike or CDC group of size 0, whereas DLP of 1 corresponds to a data strike or CDC group by 100% of users. The x-axis here shows participation rate.
Bigger means more people engaged in CDC and/or data strikes. The right-hand side here shows the underlying performance measurement that was used to calculate DLP. In this case, it was root mean squared error, the measurement used by the authors of the public implementation that we did our experiments with. Here we can see that as participation goes up, large co has less data and thus a higher, worse RMSE. Likewise, as participation goes up, small co has more data and thus a lower, better RMSE. That's the black curve on the right. This curve shows diminishing returns that we might expect to see in many machine learning and statistical contexts. Next, we can look at a similar plot showing all 4 use cases. Here we see the results are very similar for each case. In general, we see that deletion-only data strikes have very little DLP until large participation is achieved. Those are the red curves on the left. Whereas CDC scenarios, the black and blue curves, have large DLP with small participation. In other words, CDC leverages diminishing returns to create potentially disproportionate impact. Zooming in on some specific examples, in the Pinterest case, 20% of users get small co and 90% of the way to best case performance. That's the black line on the left. In the movie lens case, 50% of users get small co over 90% of the way. So we're seeing that the exact fraction of users to get performance to a certain threshold is not exactly the same in each context. In general, the trend of small or moderately sized groups often achieving large improvements in performance relative to baseline was consistent. Finally, I'll briefly discuss some implications of our experiments and the data leverage concept more broadly. At the highest level, these results suggest that CDC is a promising approach for increasing the public's ability to exert leverage against tech companies, and moreover, for creating increased competition between data-driven technologies. As we mentioned in the motivation, the stakes are high. Creating more sources of leverage can be valuable for creating a sustainable computing paradigm. Specifically, support for CDC can be highly complementary to other anti-monopolistic interventions. This means it will be valuable for future work to conduct more CDC experiments and explore avenues for making CDC easier. This might mean regulation, such as support for data portability, and it might also mean tools like scraping tools that help people collect their own personal data, or even tools to help visualize the relationships between data contributions and performance. For instance, a simple tool that displays how much a small group could help a small company improve the performance of their intelligent technologies could help motivate CDC. As mentioned before, we can't look only at DLP when thinking about the effects of conscious data contribution. Some technologies may need accuracy above a certain threshold for a variety of reasons. Ideally, we'd even directly model the cost of errors and the relationship between performance improvements and outcomes, like profit or other real-world outcomes, although this may require sensitive or proprietary corporate data. We're currently looking into new ways to approach this problem. Finally, I'll note that CDC can help change the narrative around the power dynamics between tech companies and the public. The idea of protesting large tech companies may seem hopeless, but CDC can even the odds, allowing a small group to have an outsized impact. With that, I'll end this presentation with a huge thank you to my co-author Brent, as well as the number of folks who contributed to the software and data that made this work possible. Additionally, thank you to our reviewers and many of my colleagues who provided extremely helpful feedback. Also on this slide is some of my contact info. In case you have any questions, comments, or concerns about this work, I'd love to hear them. Thank you.